Alright, so now that you know what an isotope is, let's talk about nuclear chemistry. So here are your objectives for this lecture. And let's start with this graph. So this is the graph of naturally occurring isotopes. So these are all of the isotopes that we can find in nature for each of those elements. You have this chart in your packet for nuclear chemistry. So each of the elements has about 1 to 10 isotopes in nature. And the way that you read this graph, across the bottom you have your protons, which remember tells you your atomic number, and then off to the left you have your neutrons. So for example, if we look at protons here at 60, that's neodymium on the periodic table. So you can see for all the isotopes of that element how many neutrons each one has, and then you can calculate the mass from that. So keep in mind, because I know that this was a misconception when we started, atoms don't necessarily have an equal number of protons to neutrons. The smaller ones do, yes, at the top of the periodic table, but as we get towards the larger elements, that number is going to greatly vary. So there will be a lot larger ratio of neutrons to protons. Alright, so because of this, a lot of those isotopes are considered unstable. So the larger the difference typically between neutrons and protons, the more unstable the isotope is. And when it's unstable like that, we call it radioactive. So this is typically the isotopes on that chart after bismuth, which would be atomic number 84 and up. So here's a definition of radioactive isotope for you, which is just any with an unstable nucleus and decays over time. Alright, some uses of radioactive isotopes for you. Some you're probably familiar with is carbon dating and also dating with uranium-235. And then also there are industrial and medical uses. This chart gives you a little better picture of some common radioactive isotopes that we use in medicine. So you can see things like PET scans, locating tumors, and all of that sorts of things. And then also industrial applications here as well. Okay, so let's talk about radioactive isotopes. Okay, so nuclear chemistry. What is it? Study of changes to the nucleus of an atom. So a nuclear reaction, then, is going to be a process that involves changes to the nucleus of an atom. So please don't confuse this with a chemical reaction. We're not quite there yet. They're two different things. Okay, so radioactive decay. What do we mean by this? This is just the spontaneous process during which an atom will emit or release radiation or a particle from its nucleus in order to gain stability. Typically when this is done, there's going to be a lot of energy transfer, and then the nucleus of the atom typically will be changed in some way. And the two types we're going to talk about are alpha decay and beta decay. So alpha decay first, here is a diagram for you. So you can see the beginning unstable nucleus, and then the resulting stable nucleus, and then an alpha particle being released as well as a gamma ray. An alpha particle is composed of 2 protons and 2 neutrons, as you can tell from this diagram. Well, what does that sound like? That's actually a helium nucleus. So a helium nucleus has 2 protons and 2 neutrons, and in this case we've got that just without the electrons around it, so it's not a helium atom, just the nucleus. So during alpha decay, if you look at the isotope symbols we have here before and after, notice that the atomic number decreases by 2, and also the mass decreases by 4. So that makes sense with the atomic number because we lost 2 protons. The mass also makes sense because we lost 2 protons as well as 2 neutrons. Beta decay, so again, here's our before with the unstable and after with the stable, and you can see the beta particle here. So a beta particle is actually an electron which was emitted or released from the nucleus of an unstable atom. And you're probably thinking, why is there an electron in the nucleus? Well, what actually happens is that one of the neutrons in this unstable isotope transforms and splits into a proton and an electron. That proton stays in the nucleus while the electron gets kicked out. So because of this, with that now all of a sudden a proton, the atomic number increases by 1. And since we lost a neutron but gained a proton, that mass is going to stay the same. So you can see that here. Atomic number went up by 1, the mass did not change. The gamma rays, just so you are aware of what this is sort of a byproduct of these reactions. So it's just high energy electromagnetic radiation emitted during these reactions. And these can cause damage to cells, and they're used for these purposes here. Also, to give you an idea of the difference between these types of radiations, alpha radiation is the weakest and can be stopped by paper or thin foil. Beta radiation can go through that, but can be stopped with metal sheeting or dense wood, heavy clothing. Gamma radiation can go all the way through and needs thick walls of lead or concrete. Okay, so pause for a minute and practice these. So alpha decay as well as beta decay, I give you a starting isotope, and you need to figure out what the resulting isotope would be after this particular decay. Let's talk about alpha decay together so you can sort of see how this works. So we're starting with thorium-232. Alpha decay, we said that the atomic number will decrease by 2 because we lost 2 protons. So if we look at our periodic table, here's thorium, atomic number 90. We need to go down by 2. So here's 1, this 2. So radium is going to be the new atom. And then remember that the mass will decrease by 4. So we'll end up with radium-228 will be the new isotope. So go ahead and try that for beta decay and look back at what we said beta decay was. Okay, so let's talk about carbon decay because this is important and something that we use frequently. So carbon is a radioactive isotope of carbon-14, and this undergoes beta decay to form a stable nitrogen-14 through this equation here. So this is what a typical nuclear equation would look like for a reaction. So we use this, like I mentioned before, for dating fossils and rocks and different things like that to get a relative age. So the half-life of carbon is 5,730 years. What that means is that after that amount of time, half of the carbon-14 that was originally present will have decayed into nitrogen-14. So at that half-life, you should have a 50-50 ratio of carbon-14 to nitrogen-14. Okay, so calculating half-life, let's look at how this works. Here's an example. Our original amount is 240 grams. At the first half-life, we'll be left with 120 grams. After the second, it's half of what there was before, so 60, and so on. So the first method you can use for calculating half-life is multiplication. So you can take the original amount, the 240 grams, and for the first half-life, multiply that by half. For the second half-life, you would have multiplied the original amount by a quarter of that, and then so on. The second method is to divide. So you could take your original 240 grams and divide by 2 for the first half-life. For the second, you would divide that 240 by 4, and then the third half-life divide by 8. So try this one. So how much carbon-14 will be left of a 620 gram sample after 11,460 years? So first you need to think about how many half-lives would this amount of time be for carbon-14. Alright, so the last two nuclear reactions I want to talk about are fission and fusion, which you may have heard of before. Fission is when you split apart an atomic nucleus into two smaller nuclei. This releases a lot of energy, and this is what we use in nuclear power plants. And that would look something like this. So we do this typically with uranium-235. Fusion is the opposite of that, so this is when we take two nuclei and join them together to form a larger nucleus. This releases energy as well, but a lot of energy is needed to start this reaction off, so it's not quite as efficient. And this is the process that occurs in the sun and stars naturally all the time. And here's sort of what that would look like. So you have your two smaller nuclei coming together here. Alright, and that is it. Make sure you do your practice problems.